Okay, so guys, you'll notice that the topic for your notes today is Gibbs free energy, but we're really not going to talk a lot about Gibbs free energy today. We are going to set the stage for it by quantifying entropy, and then what we're going to do is we will bring, again, the tension that Catherine brought up, this entropy-enthalpy tension. We are going to address that on Friday by talking about Gibbs free energy. So guys, today our goal, building towards Gibbs free energy, is simply to quantify entropy. So that's what we're going to do today, and then we'll bring the two together on Friday. Yeah?
Okay, sorry. So quick question. When it talks about entropy,
Yeah.
disorder can go down, right?
Disorder, and realize that for a system, disorder can go down, yes.
Okay. Or it can go up, but the entropy never goes down, right? It always goes up or is zero?
Yeah, so let's do this. Yeah, and that's the problem. So guys, let's say this, forgive me, let's say this universally, shall we? So the second law of thermodynamics simply says that for any spontaneous process, the entropy of the universe is always going up. Okay? And gosh, that's really neat. And you can think about that all you want, and that becomes fascinating. But frankly, guys, relative to this class, it doesn't matter. Okay? The thing that we care about is chemical systems. And when we care about chemical systems, and guys, this is the take-home message. When we think about chemical systems, some chemical processes, the disorder goes up. Okay, that would be an increase in entropy. For some chemical systems, the disorder goes down. That would be a negative change in entropy. Now, we've got this idea that says if the entropy of the reaction goes down, then somewhere in the universe it goes up. And that's true, but we don't care. What we care about right now is if you have a chemical reaction and when it takes place, if the disorder goes up, that's a positive change in entropy. And that happens. For some reactions, when they happen, the entropy goes down. That's a negative change in entropy, but that can happen too. We don't care about the entropy of the universe. So guys, moving forward, let's just think about the system. Is that okay? You understand is that okay? So what you said a second ago is true, but for here on out, it's unimportant. All that we need to talk about right now is the entropy of chemical reactions, and if disorder goes up, it's positive, and if disorder goes down, it's negative. And that's where you're going to live. You're not going to see questions on the test or the AP test that say if a process is, well, you might see one on this test, but never on the AP test, about if a process creates a decrease in disorder, what's going on in the universe? We just know entropy is always going up. But for our reactions, it could go down. Is that okay? You guys settled on that? Is that all right? Okay. So guys, again, what we're going to do right now is we are going to quantify entropy. So grab your AP equation sheets and let's talk. So guys, the conversation goes like this, and I don't want to create confusion, but I do need to take us back. So we are about to quantify entropy. So let's talk about quantifying enthalpy. Okay, so you ready? So guys, enthalpy, heat energy, and we talked about this idea that if we take a block, can we stick an enthalpy meter in this thing and find out how much enthalpy a block has? You can't. You can't directly measure enthalpy, so instead, what do? Well, we talk about enthalpies of formation. Do you remember that? Ashley, this is critical you get this or you're going to be screwed up for the rest of the unit. So guys, you got this idea, and I didn't mean to call you out. I just really need you to hear this bit because it's critical. So guys, are you sold on that idea that you can't directly measure the enthalpy? You can't stick a thing in here and go, what's the enthalpy of the block? Instead, we talk about enthalpies of formation, and those give us the amount of energy that's gained or lost when a mole of a substance forms. Get the idea? Okay, because guys, entropy is actually the opposite. Unlike enthalpy changes, there is no direct way to measure changes in entropy. And guys, the critical word here is changes. With enthalpy, we can't measure directly how much enthalpy a substance has, so we measure changes in enthalpy. With entropy, it's the opposite. It's hard to identify changes in entropy, so what we do instead is we directly measure entropy. So guys, how do we do that? Well, using experimental data, we can calculate absolute values for entropy for substances at any given temperature. So functionally what this means is we can pick up a block and we can say, how much entropy does this thing have? We don't need to mess around with entropy changes. We can measure entropy. And Daniel, this is about to get back to something that you were thinking about relative to the homework, and we'll get there in a second. So guys, let's talk about this briefly, but understand what we're about to talk about is not something you need to hang on to, but let's think through this. So guys, if we wanted to know the entropy of the atoms inside of this block, what kind of things do you think we would need to measure in order to calculate the entropy? Go ahead. We would need to know how many. Good. We need to know how many, because the more molecules, the more entropy. What else? The temperature. What else would we need to know? Their mass. We would also need to know their structure. Guys, disorganization is a product of how these things are associated with each other. So we would need to know their crystal structure. What else? Other things we would need to know are the strengths of the bonds that hold them together. The stronger the bond, the lower the entropy, because it cuts down on freedom. So guys, when we figure out the entropy of substances, we need to know amount, temperature, mass, structure, and the strengths of the interactions. And there are actually other factors as well. But we're never going to do this. But guys, what I'm telling you is that if you measure those things, you can actually then calculate the entropy of an object. You can calculate the disorganization of an object. If you want to look up the equations, you can Google them. You never need to know them in here. But guys, understand we can, and so we can say this block has got 1,100 joules of disorder. And we actually measure entropy in joules. So when we measure those things and do the math, and again, we never will, but when we measure these things and do the math, you can figure out the disorganization of a substance, of a system in joules. And we can actually come up with those numbers. Do you get the idea? Okay, so guys, the question then becomes, what are those numbers dependent upon? So guys, let's talk about them. So these are what are called standard molar entropies. It is abbreviated S0, where S is entropy. And guys, you remember standard means standard temperature and pressure and things like that. And guys, the units for these are joules per mole Kelvin. So there's two of the things that you guys mentioned we need to measure. Brandon mentioned how much, moles. Matt mentioned temperature, Kelvin. So guys, the disorganization of an object is actually dependent upon how much, what temperature, and then other things as well, but we don't need to worry about that. So guys, what then is this dependent upon? What are the things that determine how disorganized a system will be? And these are things that you actually need to know. So first of all, this. The disorganization of elements are not zero. The entropy of an element is not zero. I bring that up because remember the heats of formation for the elements are zero. Does that ring a bell? Or would it be helpful to go back over that? Yeah, absolutely. So guys, what we're saying is this. When we did that calculation that says delta H for the reaction is equal to the sum of N times the heats of formation for the products minus N times, I need another squiggle, don't I? N times the heat of formation of reactants. When we did these calculations, we said that the heats of formation for the elements were 0. So like if we did CH4, this was the one we did in class, CH4 plus O2 yields CO2 plus H2O, and I'm not going to balance it. But when we took these numbers and plugged them into this expression, the heat of formation for oxygen was 0 because we said that the enthalpy change for the formation of elements is understood to be 0. Is that coming back to you, Brandon? Was that enough? Yeah, guys, that is not true for entropy. The enthalpies of formation for the elements are 0, but guys, they still have disorder. So the entropies of these things are not 0. Fundamentally, guys, we're not talking about entropies of formation. We're talking about entropies. So an element can be disorganized just like any other substance. So the entropies for elements are not 0. Second thing you need to know is this. The entropies for gases are greater than those for liquids and greater than those for solids. And guys, this takes us right back to question number 3. And you may even want to reference that. 19.3 in the homework is what this point is. But guys, as you write that down, I would highlight, underline, bold, italicize, flash, whatever. Guys, this is critical. The AP authors love to nitpick this point. Nary does an AP test go by where they don't expect you to know this. We'll come back to it in a minute when I show you an example. But guys, this is critical. If you're sitting down to solve an entropy problem on a test and you're thinking to yourself, I'm not quite sure how to answer this question, the first thing that you want to ask is a phase change taking place? They love to nitpick phase changes in entropy. Number 3 is this. Entropy tends to go up with greater molar mass. What's that? Yeah, I mean, we need to be vague, but not so vague because it's actually the case. So entropy goes up with molar mass. Guys, the next one you need to know is this. Entropy tends to increase with the number of moles. This is what Brandon got at. The more stuff you have, the more disorganized it is. The next guideline is this. Entropy tends to increase with the number of atoms in a formula unit. And then, guys, finally, entropy tends to increase with elongation. And if you want an example of that, you could look at 19.6 in the homework. Why don't I make those references here? So this was 19.3, and this was 19.6. Like so. Can I do what? No, because that's going to come up in a minute. Yeah, no. I clicked too many times the first time. I don't want to get into the math until we do the concepts. So guys, let me know when you're caught up, and then we can look at an example. But frankly, my brain is scrambling right now because I don't want to give you any of the examples that have been on tests. Go ahead. Don't you worry about that none. It would be neat if I could even think of one that we could change. Let's do that. I think this will work. I've never done this before, so if this goes horribly wrong, we'll just pretend it never happened and try another example. But guys, maybe write these down with. I think this will work well. Let's let this flow. So guys, for example, let's come back to a process that is relatively familiar to us. And this time we are going to balance this. So I think I'm going to need some more space there. So 1 carbon, 2. So I need a 2, and I need a 2. Oh, it is right, but it doesn't work. Let's do this. C2H6 plus O2. Now let's balance this. So we're going to need a 3, which eventually is going to have to become a 6, and that gives us 12 hydrogens. So we need a 2, and then we need a 4, and then that gives us 8 is 6 is 14 is 7. That's better. Wow, that actually works really slick. That's cool. Okay. So guys, you get this on the test. The combustion of ethane. And the question on the test says, will the delta S for this process be positive or negative? So guys, first of all, let's talk about what that means. So what does it mean if delta S is positive? Disorder's going up. It's becoming more screwed up. Now guys, what if delta S is negative? Then disorder's going down. But guys, what you'll see in the question is they will actually give you this information. I'll put it in red so it stands out. This is a gas, this is a gas, this is a gas, this is a liquid. What's delta S, positive or negative? That's all the information you need. What's delta S, positive or negative? It's negative. Guys, why is delta S negative for this process? Because we are taking gases and turning some of it into a liquid. Guys, gases are very disorganized. If you can picture the molecules running all around in your head. Guys, liquids are less disorganized. The molecules are clumped together. Yes, they're still free to move, but they are not free to move throughout the entire container. They have fewer choices. If you think about it, when we draw gases filling the entire container. When we draw liquids, we draw them at the bottom of the container. Remember that difference between Tosok and Tazvok? Takes on shape of container and takes on shape and volume of container. Guys, gases have got more freedom, therefore they are more disordered. So if you're going from gases to a gas and a liquid, disorder's going down. Do you get the idea? Okay, now guys, I don't think I can go back far enough to make this all get cleared up. I'm gonna have to let's see. I'm gonna start undoing. Yeah, I'm not even gonna be able to get rid of the dots. Okay, so now guys, let's do this. Let's reset the stage. You may need to write this down again as well. Oh, that's a 6, isn't it? I was trying to balance it in my brain as I was going. So that we said was a 7. This is a 2. This is a 3. What did I do?
It's 2 in front of the C2H6, and then it's a 6 in front of the H2.
I thought it was C2H.
No, it's 2.
Okay.
And then H2O.
2746. 270. Got it. Okay. Are we okay? Now, guys, watch this. Again, switching colors. So now the water is not being released as a liquid, it's being released as steam. Same question. What's happening to delta S? Is it going up or going down? So guys, in order to think through this question, oh no, you can. In order to think through this question, we need to go back to this list. So guys, in our first example, we leveraged this principle. That gases have greater entropies than liquids, have greater entropies than solids, and you stood that out. Guys, in order to answer this question, it's this one. This is your second go-to. So guys, the process goes like this. If you've got a phase change, that trumps everything else. But if there's no phase change, then you fall back on numbers of moles. This is for chemical processes. You fall back on numbers of moles. So if we go over here, let's look at our example. So now we've got this. We don't have a phase change. They're all gases. So now in order to identify what's happening to entropy, we need to think about numbers of moles. So how many moles of gas do we have on the left? 9. How many moles of gas do we have on the right? What's happening to entropy, up or down? Up. Guys, moles is your secondary predictor for chemical reactions. Not yet. So guys, now let's look at these other things that are on the board. So what about molar mass? What about number of atoms? What about elongation? Guys, these are predictors that they're not going to ask you to understand relative to chemical processes. When you're talking about chemical reactions and they ask you delta S, your first go-to is phase change, your second go-to is number of moles. So when will they hold you accountable for knowing these things about molar mass, the complexity of the molecules, and elongation? Those will be comparative. So they'll give you an example like we saw in 1906, where you've got a molecule that goes carbon, 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 and then they'll give you a molecule that goes carbon, 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 and they'll ask you which one of these has a greater entropy. That's where, and I may have even drawn the, no, it's right. That's where we would say this one because of elongation. So when they want you to be thinking about complexity, mass, or elongation, that'll be just comparing two substances. When you're talking about chemical processes, then it will be phase first, number of moles second. Do you get the idea? Do you still have a question?
Yeah, so the phase is liquid to solid. Is that not included? That is gases.
No, it actually is. Solids are less than liquids. So if you had a reaction that were going liquids to solid, that would also be a negative delta S.
Okay, so
Yep.
if it went liquid to solid, but there's more moles on solid.
Good, yeah, and but it doesn't even have to be liquid to solid. Phase always trumps amount. So for example, if you're going gas to liquid, but there are more moles of liquid, it's still a decrease in entropy because phase trumps moles every time. That's a great question. You guys good? Okay, so now guys, the question becomes this. So let's go back over here, and I wonder if I can get rid of my numbers. I can't, so I'll just do this. So guys, we understand then, I think, that this would be a and I can put the numbers back up here. Guys, we understand that this is a positive delta S because the number of moles is going up, right? We understand it conceptually. The question is this: how could we figure it out mathematically? What would we need to know in order to do the math and come up with that positive number? And here's the answer. We need to know the entropy of carbon dioxide gas. We need to know the entropy of water gas. We need to know the entropy of oxygen gas, and it's not zero. And we need to know the entropy of ethane gas. And if we know the entropies of those things, what can we then do? Well, we can multiply them by the number of moles and then add them up and subtract. And if we can figure out the total entropy of these, and if we can figure out the total entropy of these, we can subtract the two and get the entropy change for the reaction. Does that sound familiar? Yeah. And guys, the equation actually looks like this. And this is, Catherine, what you wanted to see. Guys, that's the equation right there. And you know what? I'm going to add the ends. Not yet. So guys, that wasn't so good. Here's your equation. So the change in entropy for a reaction is equal to the entropies of the products minus the entropies of the reactants. This is just final minus initial. The number of moles. But guys, if you look, and maybe we should do this in the book. Sorry, I'm in the way. So does the book have it like this? It does. So guys, if you look on page 802, you'll notice that the book includes the N's. They use an N and an M, but you get the idea. These are those are the number of moles. But if you look on your AP equation sheet, you'll notice that on the AP equation sheet, they do not include the N's. Does anyone else need one? You all got them? You're okay? You're. So guys, looking on the AP equation sheet, you'll see then, this is the second equation down, and you'll notice they don't give you the N's. They're assuming that you know that you're multiplying by numbers of moles. But fundamentally, what we're saying is this. If we know how screwed up the products are, and if we know how screwed up the reactants are, if we subtract those two, that'll give us the change in entropy, the change in screwed upness for the process. Matt, go ahead. Are you sure? Okay, so guys, do you understand these ideas conceptually and then mathematically? So what will happen in the homework, we're not going to necessarily do one now because we're running short on time. They will feed you numbers and you just plug them in. Do be careful though, guys, when you do these calculations, and again, I won't be here Friday to step us through this. When you do these calculations, these numbers are in joules. Your delta H's tended to be in kilojoules. These are in joules. Both. Guys, I'm starting to really have second thoughts. So I'm getting nervous about this whole having you guys watch the screencast and take the test on Tuesday. Yeah, this is starting to make me nervous. So what do we do on what I'm really thinking about doing is, forgive me for lack of a better term, burning Friday. Oh, I get it. That's funny because this is thermochemistry. I just thought I didn't mean that. Guys, I'm really thinking about burning Friday, being with you Tuesday, and having you take the test Thursday. So, well, yeah. So here, just thinking out loud with you, what does that do? Oh, wait, no. Oh, gosh, yeah, okay, so... Oh, yeah, you'll have time. The problem is it makes my life impossible. Because I've got to have grades done right here. Right, but then the problem, is your test, your grade is based on one test. Yeah, I understand what you're saying about the retakes, but I'm not comfortable with that because the average on this next test is better than the average on the first test, simply because it's not a first test.
We're definitely going to need the retakes. But I don't know if we'll need it.
Okay, guys, here's what we're going to do. I'm not comfortable with this calendar. My wife is going to kill me. She's going to kill me. All I do now at night is grade stuff. It's like, seriously, I feel like a first-year teacher.
What if we just all
I like where your head's at. So, guys, we're going to push the test back to Thursday. We are going to wrap up the unit on Tuesday. On Friday, in my absence, you are going to summarize Chapter 6. It's not going to create confusion because Chapter 6 has nothing to do with any of this. And so it's not going to, create confusion. We're not done with today, but I really... Yeah, and so what that means then is you'll take the test Friday, Thursday. You guys stinking owe me.
next period, are you going to be in for the lab on Friday? Are you going to be in?
I will, but we're doing the lab. I know.
I was just wondering.
Yeah, sadly, I can't leverage that. Guys, let's just do that. I'll make it work. It may be the end of my marriage, but you guys can write me a note to give to my wife. Her name's Carla. Dear, with a K, dearest Carla, thank you so much for sharing your husband with us. We'll see how...
Should we all just take a field trip in Micah?
No, because actually what's going to happen is I'm going to have to give up biking up to Sundance in order to be grading your tests. Okay, guys, so we're going to put off the test. Okay, so guys, yeah, that'd be funny. Okay, so guys, this is where we're going to wrap up today. Yeah, this is where we're going to wrap up today. We're going to lay the groundwork for what is now going to be Tuesday. Understand, guys, on Friday, my sub plans are going to simply be get out of their way. I'm not going to leave plans for the sub. You guys are going to come in here and just spend that period wrapping up or summarizing Chapter 6. I'll show you the format in just a minute. It's new. But you're going to spend the period doing Chapter 6. If it doesn't take you the entire period, bring something else to work on. I'm not going to give you anything else to work on. And guys, you got to make that sub feel like they are Teacher of the Year, right? They may not be teacher of the year, but they're going to think they're teacher of the year when they walk out of here. So, guys, with that said, here's how we're going to wrap up. We are going to tip our hat, if you will, to the tension that we've just fully now created. Because, guys, we understand that we've got this idea of entropy, which is disorder. And we've talked about some of the things that help us understand what's happening to disorder during a reaction. We understand that it's dependent upon phase, and it's dependent upon amount. So, guys, we can then maybe bring these two ideas together, and we're going to start talking about spontaneity again for the last time next week. So, guys, let's have the conversation. Matt, I'm going to ignore you for the rest of the, not the rest, no, we're going to do this. So, guys, the idea then is this. In chapter 5, we learned this important idea that spontaneous reactions have negative enthalpy changes. They're exothermic. I hope that you can all sign off on that idea. If you have a problem with that statement, let's talk individually, but collectively, I hope that we can say, you bet. Balls roll downhill, methane burns, nails rust, they're all exothermic. Then, guys, we have a new idea coming out of chapter 19, and again, as Catherine got us thinking, we're done thinking grandiose thoughts about the universe, and we're now ready to think practical thoughts about reactions. And we understand this. Spontaneous reactions cause an increase in the entropy of the system. But guys, as you're thinking these thoughts, you should also be thinking about the exceptions. We saw the quick cold pack. We know that that thing's not exothermic. We know that some things happen that cause organization. A great example of that is life. Guys, life is actually a contradiction to the idea that entropy goes, because life is an organizing of things, right? So why does it happen? Well, so guys, what we need to do now is we need to bring these two ideas together. In order for us to predict spontaneity, we've got to bring these two factors together. We've got to bring together enthalpy and entropy. And guys, the bringing together of these two factors is what we call Gibbs free energy. If you're interested, the background, the historical background behind this is fascinating. It turns out that Gibbs was actually a train engineer. And I don't mean the guy that drives the train. I mean, he was an engineer that was trying to figure out how to get more work out of an amount of coal that they were burning in a train. And as he did, he started to study heat and disorder and found that trains were wildly inefficient. And he was trying to quantify that inefficiency, and that's where he came up with this idea of Gibbs free energy. That was a nutshell. I think there's more on it in your book, but if you're historically inclined, it's an interesting read. But guys, it goes like this. Gibbs free energy, which more popularly now they just call free energy. Gibbs is the one that sort of initiated the thought, but many people now just call it free energy. Guys, this is just another thermodynamic function. But what it does is it brings together enthalpy, heat, and entropy disorder. And guys, it's abbreviated G. Finally, an abbreviation that makes sense. Right? Enthalpy is H, entropy is S. Now we finally get one that works. Gibbs free energy is G. Now guys, Gibbs free energy is actually defined as this. It is the enthalpy of a system minus the temperature times the entropy of the system. But guys, the problem is that we really don't care about empirical values. What we care about is change. So huck a delta in front of each one of these, and now you've got the equation that is also on your AP equation sheet. Because the temperature is understood to be constant. What we're going to look at, though, Ethan, on Tuesday when we get back together, is we're going to talk about how changing the temperature changes Gibbs free energy. But we can only have this conversation about what's happening to Gibbs free energy if we keep the temperature the same. Then we will talk about changing temperature and how it impacts this. But when we talk about these changes, what we're talking about is reactants to products. So when reactants become products, what happens to Gibbs free energy? What happens to enthalpy? What happens to entropy? But that reaction has to stay at the same temperature to have this conversation. Okay, so guys, this then is the deal. This is your always. This is your never. This is your doesn't change. Guys, if you want to know if a reaction is spontaneous, and this is how we're going to wrap up today, you've got some ideas relative to this. You know that negative delta H's tend to be exothermic. The minute we say that, the quick cold pack is an exception. We know that entropy increasing tends to be spontaneous, but we can talk about exceptions to that as well. So guys, how do we know if a reaction will be spontaneous? And the only surefire answer is delta G. If delta G is negative, the reaction is spontaneous. Always. That's an always. If delta G is negative, the reaction is spontaneous. In the forward direction, in the direction the process is written. Now guys, what do you suppose is true if delta G is 0? It's at equilibrium. Now guys, here's the tricky bit. What if delta G is positive? Let's talk in a second. I know you're writing. So guys, if delta G is negative, the reaction is always spontaneous in the direction it's written. If delta G is 0, the reaction's at equilibrium. So guys, what if delta G is positive? Does that mean nothing's happening? It means the opposite is happening. So guys, if delta G is positive, the reaction is not spontaneous in the forward direction, but it is spontaneous in the other direction. And guys, this is where we're going to stop. So guys, again, Friday, you'll be summarizing chapter 6. I want to show you how. Tuesday, we'll wrap up the unit. Thursday will be your test. So guys, this will be the summary strategy for chapter 6. It is only chapter 6. You will, just a second. I wanted to do this first. So guys, the summary strategy for chapter 6. Let's do the pledge. And to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Okay, I need a minute. So guys, here's where we're at. Please write this down somewhere in your notes where you will have this available. This is the format that you're going to use to summarize chapter 6. You will do this for each subunit, and it will be in this order. So for each subunit, you will write down the important concepts, the important equations, and the important constants. You're going to find that this format is wildly appropriate given the content of the unit. So guys, this is the way that we're going to structure our outlines. Then in addition to that, we need to show you your homework. Guys, understand you'll be doing this with the sub Friday. Then guys, your homework is this. And again, you will not be able to do all of this, but you'll do the part that you can.
50-pound bags of potatoes